Hello, everyone. We are live with Leophilius. Welcome to my channel. Today we are going to be talking about cosmology, physics, and quantum mechanics. So this should be a very interesting show. Thank you, Leophilius, for being willing to come on. Leo, can you hear me?
Yes. Yeah, I had
Yeah.
to mute. If you were to ask me something, I had to mute the YouTube thing. I forgot to mute.
Okay, sure. So welcome again to my channel, and thank you so much for coming on.
Oh, thanks for having me. Glad to be here.
Sure. So for those of you who don't know you, can you tell us a little bit about yourself?
I am Leophilius, or at least that's what people on the internet will call me. I have an up-and-coming channel that has no videos out yet. This week I will be meeting with the YouTuber, the one and only Math Pig, who's going to teach me a little bit more. I had a meeting with a friend last night learning how to use OBS Studio, but I'm going to go through Math Pig as well because he knows some other tips and tricks and learn how to edit videos, how to do all of the producing and everything. And so hopefully by the end of this week or next week, I can get at least my introduction video for my channel up. I will be doing science education and communication on subjects like we're going to be talking about tonight, astrophysics, cosmology, quantum mechanics, as well as addressing the pseudoscience of creationism, intelligent design, climate contrarianism, anti-vaxxerism, amongst others.
Well, thank you so much. And yeah, I am completely new to editing. I really don't know much about editing, which is partially why I don't post as much as I do. And the majority of my stuff is live streams because I find that to be a lot easier. So yeah, tell us a little bit about your education background and what got you interested in cosmology and the stuff that we're talking about tonight.
Well, I have only a high school degree, a high school diploma. I was in community college for a semester in agriculture, but didn't like it. So that would be, I guess, the highest level of education you could consider myself having. I got interested in these subjects. I've been interested in astronomy essentially my entire life. It wasn't until about 10 years ago, 2010, my freshman year, that I started to get really interested in these subjects, started reading books, started watching TV shows, watching lectures. And from there, it just slowly progressed into a more and more advanced understanding of the subjects, to the point that I now have the ability of having full-on conversations with professionals, and I don't really ever get corrected, which I consider a great personal triumph.
Yeah, awesome. And I agree. I absolutely love astronomy. Astronomy is definitely one of my favorite fields of science. I actually took astronomy as an elective, and I passed it with like an 85.
Yeah.
Just for the viewers, if you have a question for Leophilius, feel free to ask in the sidebar, in the side chat. And if you are listening on my Facebook page, send me a Facebook DM, and we will get that question sent over to Leo. So I guess let's start at the beginning. For those of people who are not quite familiar with the Big Bang and what we know about the origins of the universe, why don't you start telling us in a little bit about that and what we know?
So the Big Bang is similar to evolutionary theory. It tells us about the evolution. I'm going to turn my TV down just so we don't have any sound in the background, just to be on the safe side. It tells us about the evolution of our universe from a particular point in time, but doesn't tell us how our universe came to be, as it's often worded. So it tells us that the universe evolved from an extraordinarily dense, extraordinarily hot state. And one of the biggest evidences of that is known as the cosmic microwave background, which is essentially the light left over from the period of what's called recombination, which is where photons decoupled from matter, mainly electrons. So essentially what that means is that in the very early stages of the universe, it was so dense and so hot. So the heat coming from the fact that it's so dense and it's all this matter is just compacted into a very small volume, that photons, or particles of light could not travel anywhere. It was consistently being absorbed and re-emitted by electrons. To put it into more palatable terms, the photons were essentially just bouncing off of the electrons and not actually going anywhere. Well, there was a point at which the universe had expanded enough and had cooled down enough thereby that photons could begin to free stream, as it's called, through empty space. And that wasn't until about 379,000 years after the Big Bang. So that was the moment of recombination, and that is the light that we see today, and we call that the cosmic microwave background. It is essentially observational proof of the Big Bang.
Yeah, and this is one of the reasons why I love science so much is that we're going to make a prediction based upon these models, these mathematical equations, and then voila, we find it. And
Yep.
that's the beauty of the whole discovery of science.
Hmm.
And intelligent design simply has no mechanisms or anything even remotely like this.
Exactly, and that's one of my issues with it. Everybody wants to talk about, not to digress too much, but everybody wants to talk about how there's a bias against intelligent design, and the scientists just don't like it, they don't want to use it. That's actually not at all the case. The problem is that we just have nothing to work with, and we're not going to work with models that aren't even actually models. They're just baseless conjectural assertions.
Right. In fact, speaking of which, I'm actually going to be having a debate with Antangelo on Tuesday night, and that is kind of the approach that I'm going to be taking. Instead of just repeating the same evidence ad nauseum, I'm going to actually be explaining the practical applications for evolution. We actually do have a question right now from Paul. Question for Leo: Did did the Big Bang definitely happen, or is that just one possible explanation? Thank you so much for that question.
Yeah, that's actually a pretty interesting question. Yes, the Big Bang definitely happened, but the name Big Bang is very much a misnomer because it puts an image in people's minds of exactly the opposite of what actually happened. It's not as if there was some level of explosion and then the universe was just there and it was existing. It simply means that the further back in time we go, the more dense the universe gets, the hotter it gets. And at some point, we can't go back any further, mainly because we don't have the physics to describe the structure of space time and the things inside of it at that point in time. So the Big Bang, which is today we refer to it as the lambda CDM, the letter C, D, M, and then the Greek letter lambda hyphen, the letter C, the letter D, and the letter M, the lambda CDM model. And the lambda that represents dark energy, which is the unknown form of energy that is currently driving the acceleration in the expansion of space-time. And the CDM stands for cold dark matter. So this is essentially a modification of the Big Bang model to include both dark matter and dark energy, which we know are there. We just don't know exactly what they are. But the Big Bang just tells us how the universe evolved from this very hot, very dense state as it began to expand.
And we have another question from Immutable Destiny. Thank you so much for that question. Hypothetically, shouldn't you be able to detect gravitational waves that are older than the light we can see from the CMB? That is a
Yes.
fascinating question.
Yes, it is. And yes, we should. There should be gravitational waves in space-time that are still sort of ringing through space-time, kind of like reminiscent waves. After you jump into a pool, there's still going to be some waves that kind of move through the pool from the inflationary epoch of the early universe. And those gravitational waves, at least hypothetically, should be imprinted on the cosmic microwave background. I believe it was in 2015 we thought we found that, and then it ended up being that that's not what it was. But hypothetically speaking, yes, we should be able to detect gravitational waves from the inflationary epoch, though we haven't done that yet.
Um, Thank you once again, Immutable. And here's a question from Stephen Haskins. Could the Big Bang have happened in the middle of a pre-existing universe? Now, this is kind of my understanding of the Big Bang theory, is that this is simply a point in time, and we don't know exactly how long the um, singularity actually existed for.
So could it have been? Yes. Do we have any data to indicate that? Unfortunately, we don't. We don't know if there's a furthest point back in time that we're going to be able to go past which there just literally is nothing. Like that is the absolute earliest moment of existence, or if the Big Bang is just some sort of evolutionary stage and something that's existed eternally, or if there's another universe, or if there's other universes out there. There's a lot of hypotheses of what's out there. Unfortunately, none of them have really been confirmed. I personally think that there's only this one universe, and there probably is an earliest moment that we will be able to reach that would be considered the absolute beginning of existence, if that's the way that you want to word it. But is it possible? In terms of the question, is it something that's possible? Yes, we just haven't observed anything that positively indicates it, at least thus far.
Okay, and Athena, goddess of wisdom and warfare. What do you think about the hypothesis that the universe being inside of a 5D black hole?
Well, the problem with that is that number one, we've never we don't know exactly what's in a black hole, but we know that they don't lead to anywhere else. Also, we don't know that there's any other spatial or temporal dimensions other than the three dimensions of space that we currently know and the one dimension of time that we currently know. I don't think that it's a very viable hypothesis, but that doesn't mean that it's somehow wrong.
Yeah. I honestly think black holes are probably one of my personal favorite structures in the universe just because of how bizarre they actually are.
Hmm. Yeah.
All right. Um, so let's talk a little bit, I guess, since we're on the topic of black holes, about what exactly are black holes, where do they form, and basically how do they form, and what exactly is inside them, and all that.
So a black hole is just an object that has a gravity so large that it essentially, and I'm going to keep wording things in a palatable manner, but it essentially warps space-time to the point that it curves space-time back in onto itself, which anyone who can understand sort of the basics of the geometry there would mean that nothing would be capable of moving in the away from direction off the surface of a black hole because said direction does not even exist. And this is why even photons, which have no mass and don't feel gravity, can still be trapped by a black hole, because it's not about the fact that they don't have mass or that they would need mass to be affected by black holes. It's that space-time is curved to the point that there isn't an away from direction off of a black hole, and that's why nothing escapes from a black hole. In terms of how they form, we know how stellar mass black holes form. Those form from what are called collapsars, or type 2c supernovae, I believe, which is the most massive supernovae. They're often called hypernovae, and these are formed when the core of a star collapses and it's got so much energy that it doesn't form a neutron star, it goes all the way to a black hole. As for what's inside of them, the best answer I could give is anything that's fallen in it. As far as the structure that it has, we don't know, because we don't know how to describe space-time in such extreme conditions, at least as of yet.
Okay, a couple of questions coming in this sidebar. Immutable Destiny asks, can you explain ADS-CFT correspondence and why its major point of importance in understanding early particle production and the asymmetry we see?
So the ADS in the CFT in that stands for anti-de Sitter space, and then CFT stands for conformal field theory. So this is essentially a way of combining a particular description of space-time with a particular way of describing the interactions of fundamental particles, and that's why it's called a correspondence. It is probably the most viable, and when I say viable, I don't mean that the whole model is viable, because there are numerous aspects of it, pretty much all of it, that haven't been observationally confirmed or really even experimentally confirmed. But in terms of anything that incorporates what's often been referred to as the holographic principle, the ADS-CFT correspondence, which I believe was originally developed, I want to say it was 1996, by Juan Maldacena. The holographic principle, and subsequently the ADS-CFT correspondence, tells us that four-dimensional space-time is an emergent property from the entanglement of information that is encoded on a two-dimensional lower boundary, like a light gravitational boundary or something along those lines. And it's important in understanding early particle production and the asymmetry that we see, because of the way that it describes essentially how particles interact, and the way that it would describe, if correct, the standard model compared to how the standard model of elementary particles and the standard model of cosmology, versus the ways that we describe both of those separately today.
Okay, and Paul has another question. Leo, what do you think could have caused the universe to start to expand? Also a fantastic question, I think.
So I'm going to first answer by saying that we don't know what would have caused inflation. And then I'm going to answer with what I think it could have been is probably, I should say, let me rephrase that, because we do, the thing with inflation is we know that it happened in the sense that the structure of space-time as we see it today, and the structure of our universe at cosmic scales or at relativistic scales that we see today, in almost every facet of that implies that obviously inflation happened. I mean, we could go through the horizon problem is solved by it. The magnetic monopole problem is solved by it. The flatness problem is solved by it. All of these problems are solved by pretty much only inflationary theory. There hasn't been anything else that really explains what we see, all of what we see in one theory. And what this theory states is that there would have been a particular type of field, and this would be same as like the quantum fields that we typically think of, like the electromagnetic field, called the inflaton field. And the particles of this field would have been called the inflatons. And as the universe was expanding, this field started to decay, or rather the particles contained within the field began to decay into the typical matter particles that we see today. This created an extremely gravitationally repulsive force that drove space-time apart at an extreme rate uniformly. We call that inflation. This would have happened on what's the term I'm looking for? Oh Jesus. It would have compounded, and each compound we call an E-fold. And so it would be like 2, 4, 8, 16, 32, 64, and it just continually compounds. And every time it compounds, that jump gets larger and larger and larger. That's essentially what happened during inflation. We're fairly certain inflation happened. We don't exactly know when it started, when it ended, how long it lasted, because like I said earlier, we don't have a full description of what happened in those earliest moments of the universe. The furthest back in time we can go, at least with our classical descriptions of space-time, like general relativity, is about 10 to the negative 13th seconds after the Big Bang. Anything before that, albeit reasonable, is still speculation. Are you still with us, David? I don't know if I'm the one that lost sound or if you're the one that lost sound.
Oh, I'm so sorry. I didn't realize I had myself muted.
Oh.
So Lena asks, I'm sorry if I mispronounced your name. So it was not a universe from nothing a la Lawrence Krauss. So I think this actually begs another question is what nothing actually is and whether or not nothing is even possible.
So we don't know, because what Lawrence Krauss proposes, and there are some other some other prominent cosmologists that also think the same thing, that our universe evolved out of a fluctuation in what's called a metastable false vacuum. Now, metastable is essentially a way of putting it as, say, a ball is resting atop a hill. You might say that the ball is stable, but it's actually not, because it still has the potential to roll down that hill. Even though it's not in a position where it could roll either way, it's resting there, it still has that potential. Whereas if it's sitting in the valley at the bottom of the hill, if you can picture a sombrero, kind of have that hill and then the valley would be where it's truly at rest, because it doesn't have potential to roll down that hill. So that's what metastable means. It's stable, but not really. And that's what a false vacuum is. It's a vacuum that isn't actually in its ground state. It just appears to be in a ground state, but it still has the potential to lose more energy. So it's possible that a fluctuation in a metastable false vacuum could have given rise to a pocket of true vacuum that evolved to become our universe. We don't know if this is what happened. It could be what happened. It might not be. And that's one of the problems about talking about things concerning the origins of the universe, is that almost anything you discuss is going to be hypothetical. It might be reasonable, but it is still going to be hypothetical, because we just don't have the observational or the experimental data to really give us any concrete knowledge about what was going on.
Okay, and Stephen says, so a black hole turns mass back into energy minus singularity?
Well, first, I want to comment on singularities. Singularities are not physical objects. They're a result of what happens when the limits describing something, like gravity, tend toward infinity. we call those singularities. We know that there isn't a point of literal infinite gravity at the center of a black hole, because infinites just don't exist, at least quantitatively, in physical reality, in the real world. So a singularity is a mathematical description signifying the breakdown of the math trying to describe a physical system. So singularities aren't a real thing. Whether everything inside of a black hole is energy, and the thing about that is mass is energy. It's not like mass and energy are two completely different things. They're the same thing represented in two different forms. Whether a black hole turns mass back into pure energy, I would say probably not, but as far as I know, we don't really know if that happens, but the likelihood of that being the case is probably very slim.
Okay, and Paul says, Leo, did time, space, and matter start with the Big Bang, or was there some form of time, space, and matter before the Big Bang?
And that's another one. And I'm sorry that I have to answer a lot of questions like this, but like I said just a few moments ago, a lot of this stuff is just speculation. We don't know. And so my answer to that question is we don't know. I would say, and I think that it's generally the consensus of, I wouldn't say the vast majority of cosmologists, but still the largest chunk of them, that time, space, and matter don't have a starting point. That if there is an earliest moment in space-time, that is the beginning of the universe, in the same sense that your front door is the beginning of your house. But your house doesn't physically come into existence at the front door. The whole house already exists, and the front door is just the front boundary of that house. Likewise, and we know this to be the case because time is tenseless, and we know that time is tenseless, the whole universe already exists. It's there, and it's bounded at one end, given that it does have an absolute earliest moment in space-time. But it's possible, like I said earlier, that our universe as we see it today could have evolved from some antecedent quantum mechanical regime prior to what we would consider the earliest moment of time in our local pocket.
Yeah, real quick before I get to Immutable, Paul says, Leo, don't apologize. This is great. And yeah, this is why I love science, as that we don't know, therefore we're going to find out. It's always the search for models. It's always a search for, okay, what is a viable model for this phenomena? And simply put, intelligent design has no viable answer.
Exactly.
It's just an excuse to stop thinking. Immutable Destiny, can you explain what dark flow is?
So dark flow was something that was hypothesized. I don't know how big the idea is anymore. When I first heard about it, probably would have been when I started in the 2010, 2011, maybe 2012 era, that everything in the universe is slowly actually moving toward the gravitation of what could be another universe that might be in contact, whatever that kind of contact would be, with ours, and its gravity was pulling everything in our universe toward it. And they said that there was some data to indicate this. I don't think that data has ever been vindicated, but they called that dark flow. As you can imagine, everything kind of flowing towards the gravity of that other universe.
Okay, sure. So I guess we'll move on a little bit to Einstein's general relativity, the theories. He actually has two different theories: the theory of general and special relativity, which I understand are being two distinct theories. Correct?
They are two distinct descriptions of what's fundamentally the same theoretical framework. So
sure.
Special relativity tells us what space-time is, and then general relativity tells us what happens when you curve its geometry.
Okay. And there's just so much that I love about relativity. It's, I think, my personal favorite theory in all of science, just because of the incredible predictions that was made by Einstein and his equations and all that. And then decades and even centuries later, we confirm these predictions, such as gravitational waves and the existence of black holes.
Yep. And that's one of the most phenomenal things, is that gravitational waves were predicted by the theoretical framework that he laid out, that he called the general theory of relativity in 1915. We didn't experimentally confirm their existence until 2015, 100 years later.
Yeah, and this is just how confident we are
Yep.
in these theories. This is why we are so confident in them. Now, from what I understand, is how are they that the theories of relativity and the equations derived from them are used in our technology, such as GPS and satellites. Is
So
that
with GPS, I think we do use a little bit of general relativity with those, but it's mainly special relativity in the sense that what we're doing is we're utilizing what we can know about the structure of space-time to I'm trying to think. It's not a Lagrange point, but there's a type of point that we can use along lines, obviously imaginary lines that we can draw in a coordinate space that we can run our satellites on, and they can the way that we can essentially set up our satellites. And I think our GPS satellites are actually put, and obviously they move, but they're set in a certain way that we can draw information about a point on Earth within to the inch. Actually, if we're talking agriculture, we can get sub-inch accuracy with auto guidance systems in agriculture. I know this personally because I've driven tractors that can do it from satellites that are 125. No. The GPS satellites are, I think, 14,500 miles above sea level. So they utilize special relativity to essentially hone in on points on Earth, utilizing the math of special relativity and how they move and everything like that. And the thing is that the clocks on our GPS satellites are actually ticking faster than the clocks that we have on, say, our laptops or hanging on the wall in your bathroom or your bedroom. And that is because they are further outside of Earth's gravitational field and thus experience less curvature in space-time geometry and thus less curvature of time itself and less dilation of time. This is one of the reasons that we know that time is tenseless, because under the tensed or the A theory of time, right now for us is right now for every point in the universe. But if the clocks on our GPS satellites are ticking faster than clocks on Earth, our right now is not their right now.
Yeah, excellent. And yeah, I was going to ask it. There's also with the A and B theory of time. I know Dr. William Lane Craig is a huge fan of the Kalam cosmological argument,
Mm-hmm.
which states that whatever begins to exist has a cause. Number two, the universe began to exist and therefore it has a cause. Dr. Craig himself admits that this whole entire argument rests on the A theory of time being true.
Mm-hmm.
And of course, if the A theory of time is false, then the entire argument is false.
Yeah, and this is why um, Dr. Craig rejects Einsteinian relativity. He actually does reject special relativity in favor of Lorentzian relativity, mainly what is known as the Lorentzian Aether theory, LET, which is based on there being what was known back then as the luminiferous aether. And the reason that the luminiferous aether was proposed was because sound waves need a medium like an atmosphere to travel through. Water waves need a medium, i.e., water, to travel through. Waves need some form of medium to propagate through, because we traditionally thought of waves, in a classical sense anyway, of differences in pressure in a medium that are propagating. We knew that light was a wave. So then what medium was it traveling through? It couldn't just travel through the vacuum of space, because then it couldn't be a wave because there's no medium there. So they proposed a sort of ether, a background ether, and they called it the luminiferous ether because it was the medium through which light traveled. But the Michelson-Morley experiments done in nine were those done in the late 1800s or the early 1900s? That might have been the 1890s. I can't remember, but the Michelson-Morley experiments showed that there isn't a luminiferous ether. And so that was essentially the nail in the coffin for LET, or the Lorentzian aether theory, also known as Lorentzian relativity, which was developed by Hendrik Lorentz with some help from the French, I believe it was French mathematician Henri Poincaré. So, and what they developed was that there is an absolute frame of reference, and that is the aether, but there wasn't an aether, and in fact, both Lorentz and Poincaré abandoned LET in favor of Einstein's special relativity. LET was developed before Einstein developed special relativity, and Einstein had some help in developing special relativity by Hermann Minkowski, who developed the coordinate spaces that we use in special relativity frequently. It's not the only ones, but it's the ones you're going to find frequently, called a Minkowski space. So both of the people who developed LET actually abandoned it in favor of Einstein's special relativity, which was a much simpler yet much more thorough explanation of our reality that actually explained more things. So, I mean, obviously you could apply Occam's razor and shave away, so to speak, LET, because special relativity is a better theory. It's simpler, yet it explains all of the data and then some. Also, a problem with LET is that you can't generalize it to explain what gravity is. Well, you can generalize special relativity, and we call that general relativity.
Okay, yeah, and just looking up, it was, I think, 1887
Okay,
is the
awesome.
date of that experiment. Thank you, Paul.
Thank you. Yes, thank you.
Yeah, so immutable destiny.
Yes.
Special relativity is a special case of general relativity, if I'm not mistaken.
Yep. Yep.
And Ian, hey, Ian, welcome to this one. Thank you so much for
Here comes Ian with the good question.
yeah. If you want to know more about Einstein, can I just suggest SFP mod as a good source here?
Yeah, SFB mod cites he cites Einstein about everything. It's insane.
Oh yeah.
We can talk a little bit more about SFB mod if we get to the quantum mechanics talk.
Yeah. Okay. This is actually a fantastic question. If astronauts on ISS set their watches on Earth and spend 12 months in space, would their watches' times have changed much when they return?
That really depends on how you define much, because the clocks on our GPS satellites, I don't think it's often in terms of, say, maybe, you know, the age of the universe that we have to reset them. But in terms of a human lifetime, we continuously reset them on a certain basis anyway, so that we can keep them as accurate. But their watches, when they come back, would be probably billionths of seconds ahead of the clocks that we have here on Earth. So we would be capable to a certain degree of measuring a difference there, but it's not going to be a meaningful difference at all.
Okay. Thank you for that explanation. So, this kind of leads me into the idea of the twin paradox, where one person goes at 99% the speed of light for 5 years, and the other person is like, what, 67 or whatever? So how exactly does that work?
So this utilizes something called time dilation, an effect called time dilation. And in fact, I want to say Mark Kelly, but I don't know if that's the one astronaut's name with the twin brother. They actually did this experiment with them. One of them changed while he was in space and the other one wasn't. But to take that further to what's referred to as the twin paradox is that if I had a twin and he went out on a journey for space for what would be 5 years to him and then came back, I would be significantly older than him. He would have aged what would be 5 years to him would be, say, maybe 100 or 150 years to me. I might not even be alive. And that has to do with time dilation. For him, time is slowing down just because he's traveling at relativistic speeds. And because time is slowing down, naturally, he's going to age slower, whereas I continue to age at the same rate. So and we can see this in the movie Interstellar with Matthew McConaughey's character. When he comes back, his daughter is older than he is because of the time dilation effects as a result of special relativity that are really only measurable when you reach relativistic speeds or roughly 70% the speed of light or higher.
And this is a funny comment, Ian. I just had to laugh at this. The twin paradox to me is when I met two hot Swedish twins. I wasn't sure who to date first, so I decided to date both at the same time. Let's do another paradox. Thank you, Ian.
That's funny.
Thanks
gotta love a little bit of humor.
Yep. Ian is fantastic. I love you, Ian. So let's get a little bit into quantum physics and quantum mechanics and how that differs from Einstein's relativity, because from what I understand, Einstein kind of replaced what Newtonian mechanics simply could not explain. So what exactly is quantum physics, and where does it all start?
So quantum mechanics, and I first want to explain what the word quantum means, because you'll find a lot, especially in popular science, I call it sensationalist science. People will take the word quantum, slap it on whatever they want, and say, I've got science, like quantum consciousness, or I have a nice quantum cup filled with quantum water in it, or something like that, or a quantum teleporter, what have you. The word quantum refers to a mathematical tool called quantization, which is where we find and no, why am I drawing a blank? I almost want to say Max Planck was the one who discovered through black body radiation and adding on to thermodynamics that heat energy is in fact quantized. So if you could imagine looking at a ray of light, let's say it was just like traveling in a line, and this is going to be somewhat of a contrived thought experiment. You might think that the more you zoom in on that line, you could just zoom in on it infinitely. You actually can't. The closer you zoom in on that line, you will find that it isn't a solid continuous line. It's actually made up of little discrete chunks, and there's just spaces of vacuum between them. Those chunks are what we call photons. So that means that light is quantized. It comes in discrete quanta or chunks rather than being continuous. And that's where the word quantum comes from in quantum mechanics. And what it really tells us is it just describes the nature of reality at the smallest scales in reference to that mathematical structure. And it's different from relativity in that relativity describes things on I should specify, well, special relativity does as well, but we can incorporate special relativity with quantum mechanics. We call that relativistic quantum mechanics, but general relativity is very hard to do, but I can touch on that now or later, whichever works for you.
Either way, though, before you continue, I have this fantastic quote from physicist. Oh God, I'm going to butcher the pronunciation. Devashish Singh. Yeah, I can't pronounce that. Every sentence has the word quantum in it, and it is coming out of a non-physicist's mouth. You can almost be certain that there is a huge quantum of bullshit being dumped on your head.
That's a good one.
Okay, sure. So, Paul asks, does speed have to have something to relate to? For example, if I am the only thing in existence and traveling at 50 kilometers per hour, am I actually moving? And that's a great question.
And for the most part, yes, that's true. How fast is something going? Well, you can really only measure its speed relative to something else. Like when you say your car's going 100 miles an hour, yeah, it's going 100 miles an hour relative to the Earth. The Earth is orbiting the sun at 69,000 miles per hour relative to the sun. The sun is orbiting the center of the Milky Way galaxy at 514,000 miles per hour relative to the center of the galaxy. So, technically speaking, you would still be moving. There would just be no way for you to differentiate that movement from being stationary because you don't have anything against which to measure that movement.
Very interesting. Thank you.
And that's why we call it relativity.
Interesting. Yeah. And so I guess we could kind of tackle some of the arguments made by intelligent design and creationist advocates and all. Let's start with some of their objections. What would be the consequence if the speed of light decayed over time? That's how some creationists try and get around the distance starlight problem.
Mm-hmm. There's problems that we would see if the speed of light were decaying over time, or whatever that's supposed to mean. I'm just going to take it what it means at face value. To me would mean that pretty much the whole of special relativity, aspects of general relativity, and quantum mechanics is all completely wrong and would have to continuously be updated, if we could even update it, because almost all of advanced physics is dependent on C being a constant. And all of our experiments show that C is indeed a constant.
Right, and we have to pretty much, if the young Earth creationists and young universe people are correct, which they've never been correct once in their lives, everything we know in science and all of our theories and frameworks would have to be pretty much thought over from scratch.
Yes, pretty much.
Yeah, yeah. So you can't get any more wrong than that.
Hmm.
Uh, some Now, when I was in a conversation with speed is standing for truth, um, it kind of used a very can't remember the exact words he used, but something about time dilation being used to be able to speed up the light, so it kind of warps it to us.
Oh yeah, I've heard him make that. The time dilation is like fancy math to make the speed of light stay constant, which standing for truth knows less about physics than he knows about biology and genetics, and he doesn't even know that much about biology and genetics. So that should give you a hint at how much he knows about physics.
Okay, sure. So obviously, a lot of things wrong with even his understanding of the physics behind it.
Mm-hmm. Yes, yes, very much so.
Um,
Time dilation is very, very interesting, and a lot of people, I get asked a lot, why does traveling close to the speed of light slow you down in time? If you'd like me to, I can explain it, or
oh
we
yeah,
can.
sure.
Okay.
Oh yeah, please
And I'm
explain that.
and anybody who was watching Nakasuchi, The Rage, his stream about a month, maybe a month and a half ago, when I was talking with Otangelo in there, I did the same experiment. I'm gonna, do I have to use my arm, or can I use? Do I have? Yes, I do have a pen. So I'm gonna use this pen. This pen we're just gonna imagine is a straight line in a coordinate space. This axis will be time. This axis will be space. If you were moving and we'll say that this pen represents the vector that is your velocity, your speed over a given distance. So if you are moving at 100 miles an hour, this thing is still going to be pretty much straight up. If you're moving at 1,000 miles an hour, this pen is still going to be pretty much straight up. If you're moving at 1,000 miles a second, this pen is going to slightly lean, but for the most part, it's going to be straight up. If you're moving at 100,000 miles per second, it's going to be facing like this. So as you can see, is the distance between the 2 points on this vector are short along this axis, our time axis, and longer along our space axis. So what this means is that the more you move in space, the less you move in time. So that if you're traveling at the speed of light, the vector would be horizontal. It's only moving in space. It's not moving in time at all. And that is why photons don't feel the speed of light, or don't feel time, because they travel at the speed of light. So the faster you go, the more horizontal that vector gets. So what this means is that, as you can see, the amount that you're moving in time shrinks the more you move in space. And that's what special relativity tells us. The more you move in space, the less you move in time. And that is why we have an effect called time dilation.
Okay, yeah, another argument he used, Ian brought this up, is that the Earth was in some strong gravitational well, and which explains somehow that we see stars 13 billion light years away, but yes, we're only 6,000 years old. I know I remember him using that argument in my debate, and it was like, oh my god, how do I even respond to something that is just so, what I would call, not even wrong?
Yeah, that it's not on the spectrum of wrongness. Even it's in the pits of Tartarus below that spectrum.
Yeah, that just doesn't even make any sense, because if we were in a strong gravitational well, we would obviously be able to feel it.
Mm-hmm. And we are in essentially a gravitational well of the Earth, but compared to us, yes, Earth's gravity is quite strong because we're tiny little creatures living on Earth. Compared to like the sun, I mean, if you could take your standard like SUV and put it on Jupiter, it would be flattened to literally as thin as your standard piece of paper because of Jupiter's gravity.
Yep.
And I should say not just its gravity, that would be its gravity tied with the weight of its atmosphere. So that's not just gravity, but Jupiter's gravity is quite strong indeed.
Okay, Stephen, again, thank you once again. If we are all made of different stars that are stars about 5 billion years old. If the universe is 14 billion years old, it only leaves 9 billion for a load of stars to be born and die for us here. Am I wrong? And actually, this is a great question. Fantastic question, because I see a lot of creationists try and use the divide button. Okay, there's septillions of stars. Um, their argument basically was that we have to create hundreds of billions of stars per second to get to the amount of stars we see today. Stephen, that is a fantastic question. Thank you for that.
And the funny thing is that if we were to rewind the clock 10 billion years, there were probably thousands, if not tens of thousands of stars forming every second if we're to universe into account. Yeah, so there's been plenty of time to develop the stars. He's not wrong when he says that, but we've had plenty of time to develop stars. The first stars probably don't look like the stars that we see today. It's been hypothesized that they would have been dark stars, stars that are made of regular matter, but at the center of them they're made of dark matter, and that dark matter is decaying, and the energy released from that decay is what holds the star together rather than nuclear fusion. And then those stars just collapsed into, it would have essentially just collapsed into black holes right off the bat. The earliest stars would have been very, very, very large, very bright, very hot, and thusly very short-lived. And the explosions of these stars would have helped drive further star formation, because the shock waves released from those supernovae would have helped to collapse pockets that are already dense of clouds of gas and dust to allow them to accrete matter and form new stars. And the star stuff that we're made of would be from the star that exploded about 4.8 billion years ago before our solar system formed. The shock wave from that supernova is what compacted the cloud of gas and dust that is now our sun.
Okay, and Ian, great question. I thought photons has slight mass.
They have what's called relativistic mass, but it isn't mass, it's more momentum. Everybody always says, well, if mass and energy are the same thing, then how come photons have no mass, but they're made of energy? Because energy isn't just mass. It can be mass, but it can also be momentum. And this is why anything with mass can't ever travel the speed of light, and anything with no mass must necessarily travel the speed of light, because that energy needs to be contained in the form of momentum.
Okay, interesting. Let's see here. So I know we were talking a little bit about in Speed of Sound of Gravity's channel about the accelerated Christian indoctrination program that I was forced to go to for a couple years. Just kind of wanted to look at some of the awful arguments they use from astronomy. So
I thought it'd be fun.
Oh yeah. So where should I begin?
Wherever you want.
Okay. So what is the faint young sun paradox? So by the way, for those of you who don't know, this is kind of like a comic book where there's kind of narrations. There's actually literally characters in the textbook or whatever, and so it's really it's pathetic how bad this textbook actually is. So what is the faint young sun paradox? Questions Nita. Booker volunteered to read from the exhibit report. Scientists have determined that the sun's energy is produced by fusion. The gravity of a star like the sun is so strong, hydrogen atoms are pressed together with enough force to combine and form helium atoms. When this fusion reaction occurs, tremendous energy is released. As the fusion reaction proceeds at the core of the sun, that pulls in more matter from the outer parts of the sun, causing the sun to become hotter and brighter. It is estimated that the energy output of the sun 4 billion years ago would have been 25 to 40% less than what it is now. Based on these calculations, much of Earth would have been far too cold to support life. A paradox is created for some secular scientists because they seem to hold two opposing thoughts. They think that the sun's energy output was not sufficient to support life 4 billion years ago, yet they claim that the first life appeared on Earth 4 billion years ago.
Which is really interesting, because we know that our sun was much more chaotic in its younger years than it is now.
Right. So it was, I guess you could say, always having its toddler temper tantrums.
Exactly, and then that's just how stars go. That as stars age, quote unquote, because I know it's sort of an anthropomorphization of stars, but we're limited by our language when we describe things, and oftentimes anthropomorphical analogies help us. As stars age, they lose their temperament. So, and the thing is, after the sun formed, it was probably at least a good 100 to 150 million years, if not 200 million years before the Earth formed. And I want to touch on the formation of all four inner planets, terrestrial planets, Mercury, Venus, Earth, and Mars that we have in our solar system, because it is most likely, based on the simulation models that we've ran, that those are not first generation planets to our solar system. There were originally 6 super Earths, or very large terrestrial planets, in the center in the inner solar system when it was very young. And what was happening is that Jupiter formed very, very far out. It formed further out than where it is today. So we wanted to know, because that's where gas giants typically form. They form very far out because they're gas giants. I mean, that's why inner planets are typically terrestrial, rocky, minerals, metals, whereas when you go out, it's your gas giants, because of the differences in the mass of these things, the energy of the star that is being released, and how we can push away lighter elements versus heavier elements. So we know that gas giants typically form in the outer fringes of a solar system. So how did Jupiter get where it is today? When we run simulations, what we see is that Jupiter, as it was forming, started to migrate inward, closer and closer and closer to the inner solar system. And as it was doing this, it being a very massive planet having a lot of gravity, it had essentially not a wake behind it, but sort of a wake in front of it, where it was pushing all these planetesimals and these other satellites that would have just flown into the inner solar system and would have collided with and disrupted the orbits of the 6 super Earths in the early solar system. The mass of Jupiter also would have disrupted the orbits of those planets, and they would have gone all awry. Those planets slowly destroyed themselves, collided, and all that matter spiraled into the sun. It accreted into the sun. Only about 10% of that matter was left over. And 4 very small terrestrial planets were formed from that remaining material. We call those planets Mercury, Venus, Earth, and Mars. So why isn't Jupiter all the way close to the sun, like most solar systems that have 1 or 2 gas giants orbiting very close to their stars, so close that their atmospheres are burning away? We call those hot Jupiters. Why isn't Jupiter doing that now? I mean, after all, it was migrating in to the inner solar system. That's because there was somebody else hot on Jupiter's ass, and that would have been Saturn. And Saturn's gravity tugged Jupiter and pulled it back into its stable orbit where it is today.
Yeah, and plus behind Saturn is, of course, Uranus.
Uranus, yes. I love when people say Uranus, because I'm like, it's literally not pronounced that. The Greeks would slap you if you said it that way. It's Uranus.
Yeah, Uranus.
Or is it the Romans? I think that might have been the Romans that gave it that. It's one of the two.
Yeah, I think the Uranus is the Roman god's name.
Yeah.
This gives mythology is fascinating. In Greek mythology, so, and Uranus. I'm not sure. Greek mythology. Issues here. Callius. So Uranus is Greek, and Callius is the Roman god, which is quite interesting because usually it's the other way around.
Yeah. Like Pluto and Hades, or Jupiter and Zeus.
Yeah, exactly. So yeah, that's kind of interesting to explore. So let's continue on this train wreck of a good train wreck of an argument. I lost my spot. Oh boy. Here is an exhibit about our galaxy, the Milky Way. As the other students gathered around her, she began reading the reports. Nothing as complex as this galaxy could exist unless someone made it, and that someone is God. the mass of the Milky Way is estimated to be about 3 by 10 to the 11 times the mass of the Sun. Where did all that matter come from? When one looks at the Milky Way, it is evident that matter and energy exists in the universe. Every atom and particle of matter in the universe is in continuous motion. Therefore, one can conclude that some power outside the universe must have created atoms, energized them, and set them in motion according to the laws of nature. Only God could have created matter and energy, make laws, and then put the laws into action. So yeah, this is literally what they are they are reading in these indoctrination mills.
It's just wild, isn't it? So
Yeah.
galaxies form along dark matter halos. That's why the mass can accrete into those areas. We still don't fully understand how galaxies form, but we know it has to do to the mass accretion of matter around generally a supermassive black hole that is sitting at the center of a dark matter halo. Generally, what happens is all that matter will start to accrete onto the black hole, and you have what's called an active galactic nucleus, often referred to as a quasar, if they're releasing radio jets from the poles, from the magnetic poles off that black hole. Well, this process only happens for so long. And once that black hole essentially shuts off as it's accreted all of the matter close to it, that galaxy cools down, stars begin to form, and you get something like the Milky Way. We know that the Milky Way was once an active galactic nucleus due to what are called the Fermi bubbles, which are massive bubbles of plasma that protrude outward, one going up, one going down, from the Sagittarius A star, the black hole at the center of the Milky Way galaxy. There's only one thing we know of with enough power to put that plasma there, and that's the radio jets, the relativistic jets that beam away from the poles of a black hole.
All right, and so I guess we know what causes like the stellar mass holes, but what actually causes the supermassive black holes that we see at the center of galaxies? Like, where do they?
We really don't know. A lot of people would think, well, couldn't a black hole just accrete enough matter and grow that large? No, there just isn't enough time, and there isn't enough matter, and they can't accrete it fast enough. It's likely that they started out as lower mass, like ones on the order of hundreds of thousands, if not in the lower millions, and then through merging processes and accretion slowly grew with those initial black holes, the result of the collapse of dark stars. But all of that is conjectural. We really just don't have a good idea of how supermassive black holes formed.
Okay. How do you think creationists will attempt to explain the possible life in the Venus atmosphere? Well, right now they just stick their hands in the sand and say, no, that's definitely not life.
Do you really want to know how I think they'll explain it?
God did it.
God did it. Anyway,
Yep.
The funny thing is another paper came out that said that we were actually there's probably isn't phosphine in Earth or in Venus atmosphere.
Yeah, I'm highly skeptical of any life on the Venus atmosphere. I'm very skeptical of it.
Mm-hmm. Now, if they do confirm, hey, no, there really actually is phosphine, I would bet it's probably not life. It's probably just another complex chemical process producing it that we don't know of, but it could be. But I'm after I read that secondary paper that came out, I am quite skeptical that there was ever actually phosphine in, because that's why they said it's so indicative of life, because Venus doesn't have the capability of engaging in those processes that produce phosphine, like Jupiter or Uranus or the other large gas giants that have the gravity and have the chemicals to initiate those processes to produce it. But we do know that life can do it. So if Venus doesn't have the capability of producing it through chemical processes, well, then it must be life. But now we're finding out there probably isn't phosphine on Venus, and I think that that's probably the correct answer there, is that there just probably isn't phosphine on Venus.
Right. Outside Todd, who debated Standing for Truth the other night, creationist Jack Van Imp won the 2001 Ig Nobel Prize, the Satire Prize, for demonstrating that black holes fulfill all technical requirements to be held, but they evaporate.
Yes, black holes evaporate due to something called Hawking radiation.
Right. So even in the course of quintillions of years down the road,
what I should say is that anything with mass, at least I can't speak for the quantum level. There's some people I need to talk to about that. But at the classical level, pretty much anything with mass emits some level of Hawking radiation. Now, even the most massive stars emit it at such a low rate that we couldn't build a machine sensitive enough to detect it, because the machine would be so large it would collapse into a black hole itself. And for those that don't know, Hawking radiation, first I'm going to give what is typically given as sort of an intuitive explanation of what it is that's actually not correct. And then I'm going to try to explain what it actually is. A lot of people say that, black holes, what happens is the vacuum field fluctuations that occur due to the uncertainty on spacetime that produce particle-antiparticle pairs, if those occur close enough to the event horizon of a black hole, those particles produce, one gets sucked into the black hole, and then the other one goes off into space, and that pulls mass from the black hole, causing it to shrink. That is actually not what happens. If you don't believe me, you can look it up. What happens is the energy is pulled off of a black hole by the stress of quantum fields in curved space-time. So that's essentially what's happening. It's not the particle-antiparticle pair, one falls in, that pulls mass from it. It's the stress of the quantum fields due to the extreme curvature of space-time that they're in that essentially draws energy off of a black hole, causing them to shrink or evaporate, and that is Hawking radiation.
All right. So from what I said, in the next quintillions and quintillions of years after that, would it be fair to say that all the black holes would kind of be evaporated away?
Yes.
Okay. And so then I guess this would be a fun time to talk about like the ultimate fate of the universe, which would be pretty much heat death.
Yes. The thermodynamic heat death of the universe. Unfortunately, maybe for some people, I think it is pretty fortunate, though. The universe is not going to stop existing, ever. It's not going to explode. It's not going to rip. Nothing is going to happen. What's going to happen is all of the thermodynamic free energy in the universe will be used up. Everything that exists will just slowly start to decay away. The last thing to decay will be protons and photons, being some of the most stable particles. And after that, the only thing that will exist are the fluctuating quantum fields.
Okay. And would it be possible, once that happens, that the universe process could start up again?
Under certain models, it could, but again, those models are speculative.
Right. So now let's continue with this. Let's see here. Yeah, some secular scientists have tried to resolve this paradox by suggesting that greenhouse gases in the atmosphere may have kept Earth warm enough to support life, others geothermal heat. However, there's no proof that either factor warm temperature to support life. Okay, here we go. This is this one is hilarious. This exhibit is about the magnetic field of the planet Mercury, noted Pudge as he picked up the exhibit report and read it to his friends. Prior to 1974, many scientists thought solar radiation prevented Mercury from having a magnetic field like Earth. However, when the Mariner 10 spacecraft flew past Mercury in 1974, it detected a weak magnetic field surrounding the planet. If the universe is billions of years old, the magnetic field of Mercury would have been completely destroyed by solar radiation. The existence of Mercury's magnetic field is evidence the planet is only a few thousand years old.
Yeah, that is
That
doesn't
seems to
even make sense.
that seems to be one of the things that is not even wrong.
Yeah, no, yeah, it's definitely not even wrong. I don't know much about the planet Mercury, so I don't know if it has a core that has the magneto-hydrodynamic effects occurring in it to actively continue to produce a magnetic field. It might not. I would imagine that it probably does, given how close to the sun it is, but I don't know for sure. I would bet that it does, and if it does, then the magnetic field is continually sustained, just like it is on Earth. Are there cycles in it? Of course, just like there are on Earth, but still has a magnetic field.
Okay. You know what else? Earth's magnetic field begins in Earth's core and extends as far as 36,000 miles into space. The magnetosphere protects Earth from harmful space radiation. It also protects Earth from solar winds that would strip away its atmosphere. The magnetic makes it possible for electronic and magnetic devices to work properly. Without the magnetic sphere, life on Earth would not be possible. Scientists have used gravitational bound instruments and satellites to measure Earth's magnetic field. They have also done geological studies to detect the influence of Earth's magnetic field. Based on their observations, science has concluded that the strength of Earth's magnetic field is decreasing. While the rate of decreasing is a matter of dispute, creation scientists use the decay of the magnetic field as evidence for a young Earth.
Yeah, Earth's magnetic field is not decaying.
Yeah, if we calculate for back at 4 billion years, when some evolutionists think life began on Earth, the magnetic field of our planet may have been too strong to support life. So again, this looks like that's saying that's not even wrong.
Yeah, it's not even wrong. And like I said earlier, Earth, in the core of the Earth, you have to remember it's a really, really, really hot iron and a little bit of nickel, and it's sitting in there sloshing around. Well, some of those atoms are ionized because it's so hot. So them sloshing around is going to create electric currents, and the flow of those electric currents will generate a magnetic field. That is called magnetohydrodynamics. And that continually sustains Earth's magnetic field, which does have dips in it, and the poles can reverse. It's got a cycle, but
Right.
it's been there. It's always been there. It's still
And,
there.
and we know that there has been, I think, like 167 magnetic pole reversals. It's interesting that creationists would accept one, but they don't accept the 100 plus others that we know happen for the same.
Exactly. And
So
we can detect those reversals in the stratigraphical structure of the Earth, the geological structure of the Earth.
okay, Stephen asks, seeing as there is no life on Mars, would that be a good place to try and build an environment for abiogenesis? That's kind of, I don't think that's my personal field of science, so I'll defer that to Leo.
Well, we actually don't know if there is no life on Mars. There probably could be. There may be. I think that there probably is microbial life underneath its surface because we know there's water underneath its surface, but can't be certain of that. If we ever reach the technology to, yeah, we can build an abiogenesis lab there, but it's not going to work because the amount of modification that we would have to do to get it to mimic the early Earth is going to be way beyond even what we would be capable of doing 1,000 years from now. We would essentially have to terraform the whole planet, make it look exact, give it a magnetic field like Earth's, give it an atmosphere like the early Earth's, give it the oceans like the early Earth. I mean, make sure that there's enough volcanic activity on it like the early Earth. It would just be way too hard.
Yeah, and then of course, the creation is just going to throw up their hands and say, aha, that's intelligent design by humans, ergo God. So
Yep.
that's not going to do anything for them.
Yeah, and that's how you know that intelligent design is a conspiracy theory because they are essentially saying there is no way they could be wrong because anything that demonstrates abiogenesis requires intelligence, and aha, therefore we're right. That's how conspiracy theory works. Evidence against them is actually evidence for them.
Right, exactly. And it's just ridiculous. Oh, I love this argument. Commons and creation. Even though the secular scientists, wahaha, I just love how they throw in secular scientists as like a slur.
It's funny because with the, and I just wanted to chime in here really quick, with the exception of like scientists who are explicitly creationist, even the religious scientists are secular. Secular doesn't mean atheist. It just means we're not considering religion when we do it.
Yeah, they examine the same data, they often come to different conclusions. Gee, I wonder why. There's this evidence from the conclusion that they have made concerning comets. Comets were once thought to be balls of frozen water and dust. However, experiments done after the Phyla probe landed on a comet in 2014 show that a comet contains a rocky core surrounded by frozen water, carbon dioxide, methane, and other substances. Solar winds from the pressure of solar radiation streaming away from the sun causes particles in the comet's frozen outer layer to form ions that stream away from the comet and form the tail. Because it is caused by the solar wind, the comet's tail points away from the sun. Since the tail is made up of particles from the outer layer of the comet, every time a tail forms, the comet loses part of its mass. The tail may stream out from the comet for up to 100 million miles. So a comet may lose a great deal of mass when an extremely long tail forms. The orbit of some comets begins them close to the sun's to the regularly. Several comets orbit the sun every 3 to 4 years. Halley comets every 75 to 76 years. Other comets may take hundreds or thousands of years to complete an orbit around the sun. Every time a comet comes near the sun, it forms a tail and loses some of the mass. Theoretically, when the frozen part of the comet burns off, the rocky core will continue to orbit the sun as an asteroid. However, comets present a paradox for the secular scientists. If comets lose part of their mass each time they come near the sun, and if comets have been orbiting the sun for billions of years, how can comets still have such mass after all that time? And of course, secular scientists have devised a theory to explain this paradox. Their solution was the Oort cloud. And of course, most creationists deny the Oort cloud even exists. He proposed that a large cloud of comets has been orbiting the sun at the extreme edge of the solar system since its formation billions of years ago. Comets from that far out of the sun do not form glowing tails, so even with our best telescopes, we cannot see them. According to this theory, comets in the Oort cloud sometimes pass near each other or even collide, causing their orbits to change. Secular scientists conclude that the comets we see today were once part of the Oort cloud. Um, and then they say creation scientists have a different theory. They propose that comets have their frozen layer because they were created by God at the same time and less than 10,000 years old. So
that they're just assuming that comets. Number one, they're assuming the Oort cloud doesn't exist. We know it does. We can measure its gravity and how it interacts with other planets. Number two, comets can accrete more matter. It's not like everything in the universe has a set amount of mass that it has, and once it starts losing it, it's one of those, once it's gone, it's gone. No, they can accrete more matter.
Okay, so let's talk a little bit about the evidence for the Oort cloud. What exactly are the gravitational impacts of the Oort cloud?
Disturbances on the planets and disturbances in comets, and the fact that we can see entirely new comets coming in.
Okay, and just out of curiosity, how would we know if the new comet is a new comet?
One that we haven't seen before, or if we're capable of examining its chemical structure, which we can sometimes do if we can see their tails. The color of it can indicate what it's made of. And the fact that comets don't travel interstellar. So if we see a comet that we're like, okay, well, this is new, we haven't seen this before, it's got to come from somewhere. It's not outside of our solar system. So it either came from the Kuiper Belt, or it came more likely from the Oort cloud.
And from what I understand, the Oort cloud is kind of almost halfway between the sun and the nearest star, Alpha Centauri.
Yeah, somewhere in there. It's hard to say where it starts and where it ends naturally because it's science. Yeah. I mean, there's a gradient there, but yeah, roughly.
Yeah, but it's definitely beyond the heliopause.
Yes, I do believe it sits. I believe it sits beyond the heliopause. For those that don't know, the heliopause is, oh Jesus, what is it? I keep wanting to say it's where the sun's gravitational influence ends. I think it's where the sun's electromagnetic field sort of ends. I think.
Yeah, it's where the sun's solar wind is stopped by the interstellar medium.
Yeah, there you go. Thank you for that.
Or when the solar wind strength is no longer great enough to push back the stellar winds of the surrounding stars. This is the boundary where the interstellar medium and solar winds pressure balance. So, yeah.
Yeah, just for the audience, interstellar space is not a place you want to be. It's very, very chaotic. And intergalactic space more so. So a lot, oh God, massive amounts of radiation, because there's no gas and dust, there's no stuff in there until you get close to those objects anyway that has a magnetic field to block that stuff out. It's not just Earth's magnetic field protects us from the sun, but the sun's magnetic field protects us from the harmful radiation of the interstellar medium.
Right. So I guess this is going to talk. What exactly is the interstellar and intergalactic space? Because obviously we still have, it's pretty much as close as you can get to absolute zero in the natural world.
Mm-hmm. Yes. So the interstellar medium or interstellar space is, like it sounds, the space between stars. Naturally, then I'm sure one can infer that the intergalactic medium is the space between galaxies. If you were halfway between 1.5 million miles. No, 1.5 million light years. It is between. I think that's what it is between the Milky Way and the No, that can't be the case. That can't be the case. Wait, yes, it can. Yeah, I think it's 1.5 million light years, somewhere in there. If you were halfway between the Milky Way galaxy and the Andromeda galaxy, you would be in the interstellar medium. You would be dead. Very, very, very much dead.
Right. So what exactly is in the intergalactic medium?
Electromagnetic radiation.
Okay.
That's about it.
Yeah. And that would pretty much kill you almost
The
instantaneously.
gamma rays, the X rays, the high energy ultraviolet rays. Yep. And that's why everybody says our universe is so fine tuned for us. We would die in literally 99% of places in the universe.
Yeah. Within like a fraction of a second, we'd be
Yes.
dead.
I mean, that radiation would just rip you apart, rip your genetics apart. It would be bad.
Yeah. You would be having a pretty bad day. Now, whenever a creationist uses that argument, I generally say, yeah, I agree. The universe is finely tuned to kill life.
Yes.
I mean, our own source of light gives us cancer. So,
yeah. Which I'm not even going to mention it because it kind of goes off topic a little bit.
yeah. So, what exactly, I guess, kind of trying to wrap things up a little bit, what exactly are quantum fluctuations, and are they actually uncaused?
Number one, yes, they are uncaused, and I can get a little bit deeper into that. So quantum fluctuations or vacuum fluctuations or quantum flux or quantum foam or vacuum field fluctuations, they got all sorts of names, is essentially the result of uncertainty, the Heisenberg uncertainty principle on fundamental quantum fields. Since you have uncertainty, what this means is that you don't ever have a field of energy that's just there, that's no energy. They're just ever so slightly perturbing and moving around, and we have those particle-antiparticle pairs that can sometimes spontaneously manifest out of that. And again, this is a result of just uncertainty that you can't have literally zero energy in the universe. It's just not possible. And that's what we call absolute zero, is the lowest energy state you can get, and you still have slight perturbations in the fundamental quantum fields that underlie everything in the universe. And there is no antecedent condition or set of conditions that determines when, how, why, or where any one of these fluctuations is going to take place. In the same sense that, like, a really strong breeze might slam a door shut. That's an antecedent condition that determines when, where, why, and how that door is going to slam shut. You don't have that for quantum fluctuations. The best you could say is that they have a material cause, i.e. the quantum field from which they're arising. But the thing is that most creationists try to argue, or intelligent design proponents, which is just creationism, try to argue that, well, quantum fields aren't really physical. They're not really material. So then they'd have to admit that they're at least material to argue that they're a material cause. But when we talk about things having a cause, most people are referring to an efficient cause, the thing that actively does the causing. And so wood is what a table is made from, but wood is not what causes the wood to become a table. You need an efficient cause for that. So when people say something has a cause, they're almost certainly referring to an efficient cause. But that goes into more of the four forms of Aristotelian causes.
Right. And Aristotelian logic simply has been broken down by what we know in physics. It simply is not really a good framework.
Yeah. I also say that, as an example, that weak radioactive decay is causeless, and that quantum tunneling, like when protons tunnel through their Coulomb force, or the repulsion that you would get from them because they're both positively charged, but they can still fuse in the cores of stars. That's because they are tunneling through that repulsion and then getting within range of the strong interaction, of the strong nuclear force, which is more powerful than electromagnetism, and that pulls the protons together. Generally, in the process, one of those protons captures an electron and decays into a neutron, and you can build heavier atomic nuclei through that process.
All right. Well, thank you so much for joining me. I would really like to do another stream with you and chat a little bit more.
Oh, absolutely.
I put a link to your channel in the description down below. I believe
Right on.
not, I will definitely put that down there. Yep, I definitely put a link to your channel. Good luck on it.
Thank you.
Um, am really looking forward to seeing what you produce.
I am
Uh,
really looking forward to producing it because I am going to have a lot of fun with that, I think.
oh yeah, definitely. And do you have anything you want to say before we close off the stream for the night?
Subscribe if you haven't already. You can find me on Twitter if you have a Twitter, at Leophilius, spelled the same way as you see on your screen.
Okay, excellent. And just a quick announcement: I am debating Untangelo on Tuesday at 8:30 p.m. Eastern Time on intelligent design versus evolution. It should be an interesting debate.
Oh,
Um,
yes.
yeah, Leo, I know you had some experience with him, so
I've
we can
debated him
talk.
twice on MDD. Yep.
Oh, interesting. Why don't we talk after the stream ends and we can chat a little bit about it and get me prepped.
Nope. Sounds good.
All right. Well, thank you very much, everyone. If you have not done so already, hit the like button, hit the subscribe button, and the bell notification. I am working on some music, and I'm also still working slowly but surely on the foundational fallacies of creationism series. Anyway, thank you very much. Have a wonderful